All right, chemistry, we're moving on to a new unit, very important topic in chemistry, acid-bases. Acid and base reactions are everywhere in nature, inside your body, in geology, in your car, everywhere they appear. So we're going to learn about these over the next couple of weeks. So acids produce hydronium ions. Hydronium ion is either an H plus or an H3O plus, and we'll talk about why they look different, but they're both considered to be hydronium ions. And they produce those in aqueous solution, that means water. Bases produce hydroxide, OH minus, in aqueous water. Bases are often referred to as alkaline. So acid is H plus or H3O plus, that's hydronium. Base is OH minus, that's hydroxide. So what is an H plus? Think about a hydrogen atom. It has one proton and one electron. If you take away the electron or somehow separate the proton and the electron, all you have is the proton. And that is an H plus. It's a hydrogen ion. It's a 1 plus hydrogen ion. But it's still considered hydrogen because remember, the identity of an atom is determined by its protons. And since the proton is still there, it's still considered hydrogen, but it's hydrogen without the electron, so it's an H plus. Now we're going to find out that water is at the center of this discussion. And if you take an H plus, what it will always be attracted to, or almost always be attracted to, is a water molecule, H2O. And when you add that H plus, that proton, onto an H2O, you get H3O plus because of the extra proton. There are three definitions of acids and bases. The Arrhenius definition. Now the Arrhenius definition defines an acid as a proton, that's an H plus hydronium, donor, that is, it gives the proton to another molecule, and a base as a substance that contains and releases hydroxide ions. A Bronsted-Lowry definition of an acid base is a Bronsted-Lowry definition also defines an acid as a proton hydronium donor, same as Arrhenius. It defines a base as a proton acceptor, something that takes in the H plus. The Lewis definition, which we really won't use in this class or on the AP exam, is an acid is an electron pair donor and a base as an electron pair acceptor. We might talk a little bit about those, but really in no great detail. Bronsted-Lowry is the primary definition used on the AP exam and in introductory college courses. So the acid gives up the proton, the H plus, and a base is something that accepts it, that takes it in. The Arrhenius definition is applied for strong bases. That is, they create OH minus. They have an OH minus attached to them, and they give that up in solution to produce hydroxide ions, OH minus. Acids are substances that produce hydrogen ions called hydronium ions, H3O plus. So hydrogen atoms consist of one proton and one electron and are electrically neutral. Often in natural chemical reactions, the proton is ripped away from a compound and leaves its electron behind. So it would look like that. So at this point, the proton becomes a hydronium ion. An Arrhenius acid and a Bronsted-Lowry acid are both defined as proton donors. And that word donor means they give them away. So here's a typical acid reaction. You take HCl, which is hydrochloric acid, plus water, and what will happen is the water will take that proton away from the HCl. So now the water becomes H3O plus, that is the proton added to a water molecule. You have a third proton, a third hydrogen, and since it's only the proton and not the electron, it adds a positive charge. So it's H3O plus. What happens to the hydrochloric acid is the hydrochloric acid had lost the proton. That hydrogen proton was taken away, but the hydrogen left its electron behind when it went over to the water molecule, so that leaves the Cl as a minus charge. It has one extra electron. This reaction can be written using the H plus notation for a hydronium ion. So remember, Hydronium can either be H3O plus or just H plus. So this looks a lot shorter. Let's see what the difference is between these two. They say the same thing. In the first, the reaction up above, you're using water as a reactant, and it really is a reactant because it accepts that proton from HCl and therefore becomes hydronium plus then the chloride ion. Now down below you have the HCl. You notice you don't see the water on the left side. Rather, it just says aqueous, which implies that it's in water. And what that's going to do is you're going to then have on the right side simply the H plus rather than H3O plus, and you'll still have the chloride ion presented as Cl minus. So both of those reactions represent the same thing. The one that I prefer that you use most of the time is the first one because it does show water. It shows that water plays a role in the reaction by accepting a proton. So in that case, HCl is the acid. It gives up the proton, it donates the proton, and water is the base. It's acting as a base. It accepts that proton. You'll find as we go throughout this unit, water can be both a base or an acid. It just depends what it's reacting with, but it could be either one. So the HCl donates a hydronium, that's an H plus, ion to the water molecule. Note that a strong acid such as HCl, strong acid reaction is one way or irreversible. So you see the arrow only goes one way. And we're going to talk about strong acids in just a moment. But strong acids give up, every one of the molecules gives up their proton. There's no exception. So 100% of HCl will give up a proton to a water molecule. That's an irreversible reaction because that reaction will never go back in the other direction. Once a proton dissociates from a strong acid, it never reverses and rejoins the conjugate base, and we're going to learn what that means later. Cl minus is the conjugate base of HCl, and we'll discuss that later. This is why the arrow points left to right only. It's not pointing in both directions. So H plus and H3O plus mean exactly the same thing. So there you see that they don't look the same, but the reason is because when a hydronium ion, in the absence of any other substances, when a H proton breaks away from any kind of acid, it immediately jumps over to a water molecule, and you can see that that H3O looks like a normal water molecule, H2O, but it has an added proton. It has a third proton added to it. So that's H3O plus because that proton gives it a positive charge overall. H plus and H3O plus are both called hydronium ions. This seems tricky at first because H plus is just a proton while H3O plus is a proton attached to a water molecule. This is because H plus does not simply float in water solution. In the absence of a stronger base, the H plus ion immediately attaches to a water molecule. A generic way to write this or any other acid reaction is HA plus H2O gives you H3O plus A minus. So what is that A? What's that referring to? It's referring to everything other than the proton, other than the H plus. So in the case of HCl, the A would be representing the Cl minus part of it. So you could, if you replace that A with the Cl, you'd have HCl plus H2O produces H3O plus and Cl minus. That's the reaction you saw back a little earlier. So what's the point of this notation? It's that it gives you a general way to write an acid reaction. If you're given some acid and you don't know what that acid is, you don't even know the formula for it, you just know it's an acid, you can write it as HA. So H is the proton part that's going to be donated, and the A represents whatever else is left over after that proton is gone. So you'll see examples of that and it'll make more sense. Or here's the other way, you can write the abbreviated notation. HA produces H plus A minus. H plus represents the dissociated proton, in other words it's just a proton, and A minus represents the rest of the molecule. You will use a generic equation if you are not familiar with the acid name. So all acid reactions behave the same, so they would all follow this general type of formula. Example, write the reaction for the dissociation of benzoic acid. Say, I don't know what benzoic acid is. I don't know what its formula is. All I know, if it's an acid, it must have a proton that's going to dissociate. So if you don't know the formula for benzoic acid, you can write the reaction in generic form. HA produces H plus A minus. That's the short form. Or HA plus H2O produces H3O plus A minus. You don't even have to know what the rest of that benzoic acid molecule looks like. You just know it's something, and you're just going to call that A. As long as you have the necessary values for the concentration and Ka, you can analyze the reaction for benzoic acid. So I'll quickly introduce you to Ka. That is the equilibrium constant for an acid reaction. And it's formally called the dissociation constant of acid, but it's just another form of an equilibrium constant. Here are a few more examples of Arrhenius and Bronsted-Lowry acids. So there's HClO4 produces H plus and ClO4 minus. So once that H breaks away, it leaves behind a ClO4 minus. So the generic way to write that acid is HA produces H plus and the A minus. So the A minus represents the ClO4 minus. Here's the other way to write it. You can take the long form of that reaction, and you can write it as HA plus H2O produces H3O plus and the A minus. Again, the A is the ClO4 part of it with the minus sign there. Example, HNO. So this is nitric acid. What if you were given nitric acid but you didn't know what the formula for nitric acid was? Then you could simply write it as HA produces H plus A minus. The A minus would represent the NO3 minus. So again, anytime there's literally tens of thousands of acids, and you can't know all of them. So if you just know something is an acid, you know what it means is that proton, the H plus, is going to break off, and it's going to leave something behind, some other part of the molecule behind, and that some other part of the molecule is represented by the A. So an Arrhenius base is defined as a hydroxide OH minus producer. So NaOH will produce Na plus and OH minus. So that's a perfect example. The NaOH actually has an OH attached to it. And what happens in water, our solubility rules tell us that the Na will break off, will dissolve with anything that it's attached to, so it produces Na plus and OH minus. According to the Arrhenius definition of a base, a compound must contain an OH minus that can be dissolved in water. So this is an Arrhenius base. It contains an OH minus attached to it that you can see in the molecule. A Bronsted-Lowry base is defined as a proton acceptor. So here you have NH3 plus H2O is going to produce NH4 plus. By accepting a proton, the NH3 accepts a proton to become NH4 plus and OH minus. So you see this did produce a hydroxide, and that's the definition of a base. It produces an OH minus. According to the Bronsted-Lowry definition of a base, the compound does not need to contain an OH minus the way an Arrhenius base does. However, an OH minus must be produced, but how? In other words, how does NH3 produce an OH minus if it doesn't have an OH minus? In this example, the ammonia NH3 accepts a proton H plus from a water molecule. This produces an OH minus in solution, even though the base NH3 did not contain an OH minus. So again, look at that reaction up above. Ammonia is a base. If it can take a proton away from the water molecule, then that proton will jump onto the NH3 and make it an NH4. And since the proton is positively charged and didn't bring its electron along with it, the NH4 now has a positive charge. And what does that leave behind? It leaves behind a broken water molecule. It's a water molecule without a proton, without one of its protons, but it did leave the hydrogen jumped over to the NH3. but it did leave the electron behind. So what you have now is OH minus. That's a broken water molecule. That's basically a water molecule without one proton, is OH minus. So that's how the base did that. How a Bronsted-Lowry base reaction works. So you have NH3 plus H2O, those are the reactants. NH3 does not contain an OH hydroxide ion, but one is created when H2O donates a proton. Water acts as an acid in this case because it's going to donate one of its protons to NH3 to the base. So that happens like that. So now the products are NH4 plus. You have 4 hydrogens there and one more than you have electrons. So that's an NH4 plus, and it leaves behind an OH minus. NH3 accepts a proton and becomes an ammonium ion. So NH4 plus is called an ammonium ion. Summary. In both the Arrhenius and Bronsted-Lowry definitions, an acid is a proton donor. That means it gives a proton away to water or another compound in solution. In the Arrhenius definition of a base, the base must be a compound containing OH that releases an OH hydroxide ion into the aqueous solution. And that's the definition of strong bases. So an example again would be NaOH, sodium hydroxide. It actually has an OH, it dissolves and leaves the OH minus in the solution. In the Bronsted-Lowry definition of a base, the base must accept In the Bronsted-Lowry definition of a base, the base must accept a proton from water or another compound to create an OH minus hydroxide ion in the solution. Anything that produces an OH minus in solution is a Bronsted-Lowry base. This definition covers both strong and weak bases. So let's look at how a strong acid HCl is created. All acids are made from nonmetals. For this reason, they are bonded by covalent bonds. Fluorine with 7 valence electrons is joined by hydrogen with 1 valence electron, so the hydrogen comes over and joins on, and that creates hydrochloric acid. Both atoms fulfill the octet rule to create a covalent bond, and that's HCl hydrochloric acid. We now have a strong acid that will react with water. Acids are divided into strong acids and weak acids. A strong acid is one in which all of the H plus protons break away from every acid molecule and then they jump onto a water molecule or some other molecule, but usually it's water. So a weak acid is one in which only some, not all, of the H plus protons break away from every acid molecule. So when a proton, H plus, breaks away from its acid, it is said to dissociate. Dissociation occurs because the hydronium H plus proton is more attracted to one of the lone pairs of electrons on the water molecule than to its own chlorine atom. So hydrochloric acid, HCl, is a strong acid. All HCl molecules in an aqueous water solution will donate their H plus, their protons, to a water molecule like this. There it goes and it jumps over there. So the hydronium ion now can be written as either H plus or H3O plus. But as you can see, it really is H3O plus, and that's why we prefer to use that notation. The dissociated hydrogen leaves its electron behind. So that gives the chlorine a negative charge now. So the chloride ion Cl- remains in solution. An acid produces a broken hydrogen atom. That's what happened. The proton jumped over to the water molecule of the hydrogen, the proton of the hydrogen, and left its electron behind. So you broke a hydrogen atom in two. A Bronsted-Lowry base accepts the H plus hydronium ion released by the acid. In this example, water acts as a base by accepting the H plus ion donated by HCl. The proton attached to the water produces a positively charged H3O plus ion. An H plus ion is the same as an H3O plus ion. Both are called hydronium ions because the proton immediately attaches to the water molecule. It doesn't just swim around in the solution by itself. It comes off of the hydrochloric acid and immediately jumps on to the lone pair of a water molecule. So there's the hydronium ion. So when the H plus proton is pulled away from the Cl minus, it immediately attaches to H2O. So H plus and H3O plus are both referred to as hydronium ions. So there you go. Those are both, you can use either of those notations. The H plus really technically is just the proton, whereas the H3O is a proton attached to the water molecule. But in chemistry, we treat them as though they mean the same thing. The AP standards prefer this symbol for hydronium, and so do I, because it really reflects what you're seeing there, is 3 hydrogens and 1 oxygen. A strong acid is one in which all of the H plus protons dissociate from the acid. So if you put a million hydrochloric acid, which is a strong acid, hydrochloric acid molecules in water, all 1 million are going to give up their proton to each one to a different water molecule. There are 7 strong acids, and you should memorize these: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. Some references don't list this as a strong acid, but the AP textbook that we use at this school does. All strong acids completely dissociate in water. So every time you put a strong acid molecule in water, that hydrogen proton, that hydronium, is going to break off and jump over to a water molecule. All other acids are weak acids and do not completely dissociate. So the reason you memorize the 7 strong acids is because there are, as I said, tens and tens of thousands of acids. And if you know the strong acids, then anything that's not one of those 7 is a weak acid. In other words, it's only going to partially dissociate. Some of the molecules will give up their proton, but not all. And it's usually a very small fraction that will do it. There are several other ways acids are classified. So these are the 7 strong acids again. Now the first 3 are called binary acids because they contain 2 different elements: hydrochloric, hydrobromic, hydroiodic. So acids with a hydrogen attached to a single halogen, you notice all 3 of those are halogens in the second to last column of the periodic table, are called binary acids. Down below, the acids with hydrogen attached to an oxygen compound are called oxyacids. So nitric, sulfuric, perchloric, and chloric acids are oxyacids. Acids with more than 1 hydrogen, such as H2SO4, are called polyprotic acids. Polyprotic means many protons. When the proton from HCl dissociates, it leaves behind a chloride Cl- ion. A negatively charged ion can attract an H plus hydronium ion, making it a base. Here, Cl- is a base. What remains behind is the negatively charged Cl- ion. The H plus, in the absence of any other substances, attaches to the lone pair of a water molecule to become H3O plus. The base that differs from its acid by exactly 1 proton is called a conjugate base. So hydrochloric acid, that's HCl, and the chloride ion Cl-, the only difference between them is that 1 proton that dissociated. So that's called a conjugate acid-base pair. The HCl is the acid and the Cl- is the base. A conjugate acid and its conjugate base are called a conjugate acid-base pair. Think of a conjugate acid-base pair as brother and sister. They are related. A base that differs from its acid by exactly 1 proton is called a conjugate base. Hydrochloric acid, HCl, and the chloride ion, Cl-, are a conjugate acid-base pair. So there you see the conjugate acid of Cl- is HCl, and the conjugate base of HCl is Cl-. The only difference between those two is that one blue proton there. A conjugate acid-base pair are called acid-base. A conjugate acid-base pair are an acid and base that differ from each other by exactly one proton. Examples of acids and its conjugate base are hydrochloric acid, which is HCl. The conjugate base is Cl-. Nitric acid is HNO3 and NO3-. They only differ by that one H, that one proton. Acetic acid is CH3COOH and CH3COO-. So the proton went away, left its electron behind there, and made it a negatively charged. That's called an acetate ion. The importance of conjugate acid-base pairs will be seen later on. A conjugate acid-base pair is an acid and base that differ from each other by exactly one proton. Examples of bases and its conjugate acid are ammonia, NH3. The conjugate acid is NH4 because it took on a proton. Now it has an extra proton that it can donate in the future, making it an acid. Bromide, Br-. Now if it takes on a proton, that's hydrobromic acid. So that's a conjugate acid-base pair. Chlorate is ClO4-. It takes on a hydrogen. That makes it HClO4. The importance of conjugate acid-base pairs will be seen later on. So let's look at the strong acids quickly. We're going to look at all 7 of them and what happens. So this means that every strong acid molecule that enters the water will give a proton to the water molecule. So this is hydrochloric acid. There goes the proton over to the water molecule. All HCl molecules donate a proton to a water molecule. Here's hydroiodic acid. It's going to give up its proton 100% of the time. There it goes, and now it produces all HI molecules donate a proton to a water molecule. There's hydrobromic acid, and it's going to give away its proton. There's nitric acid, and it's going to give away its proton. Okay, here's sulfuric acid. Now notice it has 2 protons. So sulfuric acid is H2SO4. All H2SO4 molecules donate a proton to water. When the first H+ dissociates, the resulting compound is hydrogen sulfate, HSO4-, which is a weak acid. The second proton will dissociate sometimes, but not always. That's the definition of a weak acid. It doesn't always 100% of the time dissociate. The second dissociation produces the sulfate ion SO4 2-. So we saw that on the 60 common ions. What's sulfate? It's SO4 2-. That's how it's formed. It's formed by dissociating acids. So here's perchloric acid, HClO4. It gives up the electron, and all HCl4 molecules donate a proton to a water molecule. Here is chloric acid, HClO3. It donates a proton to the water molecule 100% of the time. Now, strong bases are bases that completely dissociate in the same way as strong acids. Here is a list of strong bases. LiOH. We know Li dissociates with anything that it's attached to. So does NaOH. So does Na. So does potassium. Rubidium, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So notice all of these have hydroxides attached to them, which will dissociate into the solution to produce a base. So a base solution is one that has OH- hydroxide ions in it. So there are those elements, strong bases, so they contain hydroxide ions. They contain alkali or alkaline earth metals. They dissociate 100% like strong acids. So you notice the position of the metals and the strong bases form the letter B on the periodic table. So that's one way to remember them. So what determines the acidity of a solution? The acidity of a solution is determined by the concentration of hydronium ions, H3O+, and how many there are in a solution per mole. Okay, so strong acids. So what determines the acidity of a solution? The acidity of a solution is determined by the concentration of hydronium ions, H3O+, are in So strong acids. What determines the acidity of a solution? The acidity of a solution is determined by the concentration of hydronium ions, H3O+, in 1 liter of solution. So it's a concentration. Though this is a less acidic solution, this is a more acidic solution, assuming those volumes of water there are exactly the same. All right, that takes care of our introductory lesson. A little bit long, a lot of terminology, no math, so just learn these definitions because we're going to use them almost every day for the next 2 weeks.